Hello everyone, welcome to Maths Easy. Today we are going to discuss about another important aspect in A-level physics, that is how to figure out the current that flows through a given branch when you have a situation like this. So here we have current capital I flowing into the junction, and then it splits up into two components I1 and I2 through different resistors R1 and R2. Now this technique, which helps us to quickly figure out the current that goes through each branch, is very helpful in A-level physics. Now let me show you how this works. So we know, imagine if R1 was smaller than R2, then for the current R1 is an easier path to go. There's less resistant path. So what will happen? A larger proportion of capital I should go through R1, which means the current splits such that it's inversely proportional to the resistors. So for that reason we can directly figure out the two formula here. I1 is equal to, you get the other resistor. What's the other resistor? R2 over R1 plus R2 times by incoming current capital I. Similarly, if you want to get I2, what should I do? I get the not that resistor, the other one, R1 over R1 plus R2 multiplied by capital I. Now this is a very useful technique so that you can figure out the current that is going through a certain branch straight away. Now I'm going to show you this with an example how it works. Alright, now let's look at this example. The current I1 and I2. So you need to work out these two. We know the current that comes in is 10 amps and this resistor is 2 ohms. This resistor is 3 ohms. Okay, so let's use this formula. I1 is equal to, what do we do? The other resistor 3 over the sum of the resistors 3 at 2, 5 times by the incoming current 10. I2 is the other resistor because it's inverse, 2 over 5 times by 10. Now that's 4 amps and that one is 6 amps. Now you can clearly see, once you figure that out, when this current here is 6 amps and when this current here is 4 amps, what's the voltage across this one? Voltage across this one is V equals IR, 2 times 6, 12 volts. Again for this one, 4 times 3, 12 volts. Now you can clearly see that should be the case because these two are in parallel. So the the voltage difference across both should be exactly the same. Let's try another question. In fact, this time I'm going to get a question on the board. I want you to pause the video and see if you can use this technique to figure out the current. Okay, here's a new question. Can you please pause the video and give it a try? I will get you the answer in a minute. Right, let's use the same technique. To get I1, we need the other resistor, which is 15, over the total resistance, which is 15 add 5 is 20, multiplied by 12. Now that gives me 9 amps. Let's try the other one. To get I2, the other resistor, which is 5, over the total resistance 20 multiplied by 12, and that gives you 3 amps. Now you can clearly see 9 add 3 gives you this 12. So that means the conservation of charge that's working. Now if you get the potential difference across this one, V is equal to IR. That is 9 times 5 is 45 volts. If I use it across this one is 3 amps. 3 times 15 is again 45 volts. So we can see definitely this is right. Now this is a pretty useful technique when you want to see what's the current going through this, because you get circuits like this, like parts of circuits where you have an incoming current and it splits in between two resistors. This is very useful. There are other ways of doing this as well, but I would say this is a pretty useful technique. Now, if you wonder where this result come from, here's how you actually theoretically prove it. Now, we know for the top branch, V is equal to I1 R1. Similarly, for the bottom branch, it's V is equal to I2 R2, but it's the same voltage. I1 R1 is equal to I2 R2. So, also I know because of the conservation of charge, in fact it's Kirchhoff's first law, the current coming into a point is equal to the current, sum of the currents going out from that point. So capital I is equal to I1 plus I2. Now from the first equation I'm going to make I2 the subject. So I can write from this one, I2 is equal to I1 R1 over R2. Now I'm going to substitute this for my I2. So I get capital I is equal to I1 plus I1 R1 over R2. Now let's simplify this a little further. I is equal to common denominator R2. I have to multiply top and bottom by R2. So I1 R2 plus I1 R1. Now let's move this R2 to this side. I get IR2 is equal to I1 R2 plus I1 R1. Now you can clearly see I can factorize I1 on the right hand side. This I1 and here's I1. So let's do the factorization. IR2 is equal to I1. I got R2 plus R1. I'm going to switch the, it doesn't really matter, like R1 plus R2 and R2 plus R1, they are the same. So I1, R1 plus R2. Now let's make I1 the subject. You get I1 is equal to IR2 on the left hand side divided by R1 plus R2. So if I just rearrange it a little bit, I get I1 is equal to IR2 over R1 plus R2 multiplied by capital I. Now this is what we used earlier, right? This is the theory part of this one. Sorry, that went a little out of sight here. Now, so to get I1, this one here, what do? R2 over the sum of the other two resistors. R2 over the sum of the resistors multiplied by I. So that's how it works. But I just explained the theoretical approach at the very end, but you don't really need that to use this one. All you need to do is how I showed you in the first couple of examples.